Hi, my name is Srinivasan. I'm at Aarhus University, and I want to tell you something about our recent work on constructing optimal small depth circuits for the coin problem. This is joint work with Utkarsh Tripathi at IIT Bombay. Let me start by defining the coin problem. Uh, so it's an extremely simple problem in computational statistics, or more generally in computation. So the basic problem is about estimating the bias of a coin. So more formally, the setup is as follows. So you have a coin which comes up heads with some probability that I'll call B for bias. And we are given that this bias is either slightly more or less than a half. Yeah, and the distance from half is captured by a parameter that we'll call delta throughout. And what we'd like is an algorithm that kind of predicts the direction of the bias correctly with high probability. So we have an algorithm that takes as input a bunch of independent coin tosses of this coin and says yes with high probability if the bias is towards heads or towards one, and it says no with high probability if the bias is towards tails or towards zero. Okay, and so this is the basic problem, and we want efficient computation procedures for this problem. Yeah. So if you think about this for a while, you immediately come up with the following procedure, which is to take a simple majority vote. So what you could do, for instance, is to take a bunch of independent coin tosses of this coin, so something like 1 over delta squared many coin tosses would do. And if you see more heads than tails, then you predict that the bias is towards heads, and otherwise you predict that the bias is towards tails. Right? So this is a fairly simple procedure, and it's a simple application of Chernoff of the Chebyshev inequality, which will tell you that this procedure indeed solves the delta coin problem as stated. Okay. So we're going to look at various procedures of this form, and in particular, we'll be interested in two facets of such procedures. We'll be interested in the sample complexity of such procedures, which is the number of coin tosses they need. And it's a folklore kind of information theoretic fact that any procedure that solves the delta coin problem needs at least a 1 over delta squared many such coin tosses, which means that this very simple majority vote is in fact sample optimal. Okay, so that's great. Another facet that we'll be interested in for such procedures is the computational complexity of such procedures. So we'll be interested in algorithms that can be carried out in extremely restrictive models of computation. And these models of computation are so restrictive that computing something like a majority vote of so many coin tosses is in fact prohibitively expensive. So in such situations, we'll be interested in in finding out what is the most resource efficient way of solving the coin problem. Okay. And the particular resource that is important to us in this work is that of Boolean formula size. So we look at Boolean formulas with a certain set of gates, and we ask what is the smallest formula that solves the delta coin problem. Right. Okay, so that's the setup. So now why are we interested in this problem? Well, it's an extremely simple computational problem that sort of shows up in very different scenarios for all sorts of different reasons. So it plays an important role in understanding some hardness amplification procedures. It comes up in interesting situations in studying metacomplexity, in cryptography, in streaming lower bounds, etc. And the particular application that motivates our work in this paper is an application towards proving certain circuit size hierarchy theorems. So we all probably know about time and space hierarchy theorems, but in this situation, we are interested in proving size hierarchy theorems for families of Boolean circuits. And the interesting classically studied families of Boolean circuits for which the only such hierarchy theorems we know how to prove are via studying the coin problem. Okay, this was observed in this work of LSSTB, which is the two of us, along with some co-authors from a few years ago. And so in this work, we sort of strengthen one of the main theorems of LSSTB and hence derive improved hierarchy theorems. So let me start with a brief description of LSSTB, and then I'll tell you our result. So what is it that LSSTB do? So they study the complexity of the coin problem in the setting of AC0 XOR or AC0 mod 2 formulas. So these are Boolean formulas that are made up of AND, OR, and XOR gates, right? And we are typically looking at formulas of constant depth or slowly growing depths. Okay, so small depth formulas. And it's well known that such formulas cannot compute the majority function efficiently. And the aim here is to understand how well these can solve the coin problem. What are the smallest formulas that solve the coin problem in this model? Right. And so in this context, LSSTB prove two theorems. The first is a kind of a lower bound. So given a depth D AC0 mod 2 formula that solves the coin problem, they show that the size of this formula is at least this quantity. So this is some sort of exponential function in 1 over delta, right? So which means that there are no super efficient formulas for solving the coin problem. right? So there's some sort of exponential lower bound. And the second theorem that LSSTV prove is a matching upper bound. So they come up with explicit depth D monotone AC0 formulas. So these are formulas that don't use XOR gates at all. They just use AND and OR gates. They're depth D formulas of this kind that solve the delta coin problem. And moreover, their size bound roughly matches the lower bound up here. Okay, so these are not exactly the same bounds. I've omitted some fudge factors in the exponents, but up to a polynomial, these are the same size. Okay, so there's some constant factors that are missing in the exponents in both cases, but up to that, they're the same. Right. So what this means is that up to a polynomial, we have optimal upper and lower bounds for solving the coin problem in this model. And interestingly, these are the only problems for which, as far as I know, we have matching upper and lower bounds. Okay, so the coin problem is sort of the only problem for which we have matching upper and lower bounds in this very classical circuit model. Okay. And so why is that important? Well, the reason it's important is that as soon as we have optimal upper and lower bounds for a problem, we get sort of hierarchy theorems for that model, right? And the reason for this is that a hierarchy theorem essentially tells us that for some resource, having access to more of that resource gives us more computational power, right? And in particular, for the coin problem, we see that it cannot be solved in this size, but it can be solved in this size, which means having access to some slightly more circuit size allows us to solve a coin problem that we could not solve with smaller size. So it witnesses a difference in the computational powers between these two models. Okay. Yeah, so we get hierarchy theorems as a result of these upper and lower bounds. And it turns out, which is something that I've hidden in my description of these theorems so far, is that the strength of these hierarchy theorems in some particular sense that I'll make precise in the next slide, the strength of these hierarchy theorems is dictated by the number of samples of these underlying formulas. So it sort of depends on the sample complexity of these underlying formulas that are constructed in theorem. So what is the sample complexity of these formulas? Well, it turns out that the sample complexity of these formulas constructed in this work of LSSTV is something like 1 over delta to the t. Yeah. So for constant d, there's a polynomial function 1 over delta, which is pretty good, but it's still a far cry from the information theoretically optimal 1 by delta square. Right, so the simple majority wood has an information theoretically optimal sample complexity of 1 over delta square, but this is something that's slightly worse. And what's more, it's a little bit counterintuitive that as the depth of the formulas increases, the sample complexity actually grows, because we think of increasing depth as making the model stronger. So it's strange that more depth requires more sample complexity. Okay, so it's a sort of counterintuitive, and it also means that our hierarchy theorems are sort of weaker than what one might hope for given the current state of circuit lower bounds. Okay, so in this work, what we do is we fix this facet of LSSTV. Our main result is a kind of a sample optimal construction of formulas for the coin problem. Yeah, they continue to be explicit, size optimal, and monotone AC0 formulas, but now they also use an information theoretically optimal number of samples, 1 by delta square. Okay, so that's the main result. And the corollary of this, almost immediately following the same idea as LSSTV, is an improved hierarchy theorem. And the improvement is in the sense that the hierarchy theorem now holds for the entire size parameter regime where we have lower bounds, right? So this the model of AC0 mod 2 formula is a kind of classically studied circuit model, and we've had lower bounds for these for this model for a while now. And the previous hierarchy theorems, however, could not prove did not hold in the entire parameter regime, size parameter regime, but we had lower bounds. And this was essentially down to the fact that the sample complexity of the formulas that we constructed was suboptimal. And now with this optimal sample complexity, we actually get lower bounds in the entire parameter regime up to the size, the maximum size where we actually have circuit lower bounds. So one cannot improve our hierarchy theorem, presumably, without proving new circuit lower bounds. Okay. So that's kind of an immediate corollary of our result. And there is one caveat, though, with our result, which is that we need to assume some sort of relationship between the parameter delta and the depth of the circuit. So in the situation where the depth of circuit is a constant, this is not really a restriction of any kind, but in the situation where the depth is a constant, it's not a restriction of any kind, but when the depth becomes a super constant, this is some sort of restriction, and maybe this can be removed in future work. Okay, so that's it. So that's the statement of our main result. Now let me tell you a little bit about the techniques that we use. All right. So in terms of techniques, you would think that given that we build we build and strengthen this work of LSSTV, that our techniques would be closely related to the techniques of that paper. But in fact, they diverge from that paper at a fairly fundamental level. Yeah. So at a very high level, the work of LSSTV was based on de-randomizing a certain randomized construction of formulas solving the coin problem. Yeah, and so how did this randomized construction come about? Well, there are older works of O'Donnell, Wimmer, and Amano that show that there are certain read-once AC0 formulas that solve the delta coin problem that are of optimal size. Right? So we have optimal size read-once formulas that solve the delta coin problem. The unfortunate thing about these constructions is that they are read-once formulas, which is to say that every leaf is a distinct variable. Yeah, and since these formulas are of exponential size, right? Recall that the lower bound for these for solving the coin problem is already an exponential lower bound. So these formulas are necessarily of exponential size, and since they're read-once formulas, they also have exponential sample complexity. Right. And since they have exponential sample complexity, it turns out they don't give us anything in the way of hierarchy theorems. Yeah. So what LSSTV sort of observed was that by duplicating, by subsampling this set of exponentially many variables, by replacing them randomly from a smaller set of variables, you still get a formula that solves the coin problem, but with much improved sample complexity. And when can view the final deterministic construction of LSSTV, the explicit construction, as a de-randomization of this probabilistic construction. Okay, so that was essentially what LSSTV did. And in this work, we sort of deviate from this paradigm by de-randomizing instead a different randomized construction. Right? So we instead look at a random circuit construction, and this random circuit construction for the coin problem is due to work of Ben Rossman and myself from a few years ago. And what we showed there was that we could come up with better circuits for the coin problem. So recall that circuits are a stronger model than formulas in some sense, and we showed that we could come up with better circuits for solving the coin problem. Yeah, and again, our construction was randomized. And in this work, what we do is we try to de-randomize the circuit construction that we had in the work of RS. Unfortunately, we are not able to do this optimally. So our de-randomization of the circuit construction is in fact suboptimal in some way. But the strange thing about it is, despite the fact that this de-randomization is suboptimal, when we unfold this random circuit construction into a formula in an obvious way, we get an optimal sized formula. So despite the fact that we have a suboptimal de-randomization of the circuit construction, we end up getting an optimal de-randomization of AC0 model formulas. Yeah. So that's sort of kind of a fun and unexpected result of our de-randomization of RS. Yeah, and it's so one of the main open problems that kind of remains after our work is to de-randomize the circuit construction of RS optimally. Okay. So now let me tell you a little bit about this construction of RS, and then I'll get to the main de-randomization that we do. Okay, so how does this construction of RS work? So this construction itself builds upon an older circuit construction of Huri, Magen, and Pitassi. And so it sort of works roughly as follows. So we construct this circuit. So imagine that this is a depth D circuit. So it's a kind of a layered circuit. So we start with the variables at the base, and these variables sort of indicate the coin tosses that we get. So we start with an information theoretically optimal number of coin tosses. So each of these variables is 1 or 0, depending on whether the coin comes up heads or tails. Right, and then we have a layer of AND gates, then we have a layer of OR gates, and AND gates, etc., until we construct a depth D circuit. Right. So we have alternating layers of AND and OR gates. And now in order to tell you how to consider what the circuit is exactly, I need to tell you how many AND and OR gates there are at every layer. Right. And it turns out that the number of gates in every layer except the first and the last is essentially the size of the circuit. So it's roughly this exponential quantity that we've been talking about. And finally, how are these gates connected to each other? And this construction, this is where the circuit becomes randomized. We essentially put in a random graph between every pair of adjacent layers of the circuit. Okay, so we decide beforehand what the fan-ins of all of these gates are going to be at any given layer, right? And let's say the fan-in of these gates at layer 2 is some number D. Then each gate essentially chooses D gates from the previous layer and sort of makes those the children of this gate. Okay, makes those its children, and that's how we can kind of construct the circuit between these two layers, and we do this between every pair of layers of the circuit, and that gives us the construction of the overall circuit. Okay, So it's kind of a randomized construction. And now in order to de-randomize it, we have to sort of understand why this random construction works, because that tells us what we need our explicit construction to do as well. Okay, so let me just try to describe that, and then I'll tell you how we de-randomize it. So why does this random construction work? So imagine that we are trying to use this circuit to solve the coin problem. So the circuit is supposed to distinguish between the case when the bias is slightly more than half, so half times 1 plus delta, and the bias is half times 1 minus delta. So those are the two cases. So now the number of samples we have at the base, the number of variables we have in the circuit, which is the number of samples in this coin, is this quantity 1 over delta squared, right? So by a simple application of the Chernoff bound, we know that the number of ones among these variables is going to roughly reflect the bias of the circuit. So a number of ones is going to be a fraction which is half times 1 plus or minus delta, depending on the bias, right? So that's kind of the base case of this. And so now what happens at layer 1 of the circuit? So let's imagine that each of the AND gates at layer 1 is a gate of fan in M, right? And now what we are going to do, the way we're constructing this circuit, is that so right now it's a randomized construction. So each AND gate chooses M of these variables at random and makes those its children, right? So which means that each AND gate is set to 1 with probability roughly 1 over 2 to the M, but it's 1 over 2 to the M times a factor that depends on the bias, the exact bias of the underlying variables. And you can see that now a simple calculation shows us that it's now 1 over 2 to the M times 1 plus or minus delta times M. Okay, so it's not 1 plus or minus delta, but more like 1 plus or minus delta times M. Yeah. And so now this is in some sort of sense progress, because in this case, the difference between the two biases multiplicatively was 1 plus delta versus 1 minus delta. And now that same delta has been replaced by delta times M. So multiplicatively, the difference between the two biases has increased, right? So that's the probability of each AND gate being set to 1. And again, by a simple Chernoff bound, this is roughly the fraction of AND gates that are set to 1 at this layer. And so now the difference between the two biases is sort of blown up by somewhat from delta to delta times M. And this kind of process continues. So the next layer, the bias increases, but instead now the bias is determined by the number of OR gates are set to 0 rather than the number of OR gates are set to 1. And this kind of phenomenon repeats itself through all the layers of the circuit until the end, where the difference in the bias is a large constant, at which point we've solved the coin problem. Okay, so that's sort of how the RS construction works. And now in order to do this construction deterministically, we essentially have to simulate this property of a random graph between two layers of the circuit deterministically. Yeah, and this leads us very naturally to this notion of a neighborhood complement graph. So what's a neighborhood complement graph? So you can think of these as two adjacent layers of the circuit. So imagine that U is some set of some layer of the circuit, and V is the next layer, let's say made up of AND gates. Yeah. So now, when does a gate in V evaluate to 0? When does a gate in V evaluate to 1? It evaluates to 1 exactly when it has no neighbors among the gates in U that evaluate to 0. Okay, so they're essentially in the complement in the neighborhood of that set in U, right? And so what we would like is that the fraction of gates that evaluate to V, that evaluate to 1 in V, to sort of reflect the fraction of gates that evaluate to 0 in U. Okay, so that's sort of what we'd like to happen. And this leads us to this definition of a neighborhood complement graph, which is defined as follows. So imagine that we actually choose a graph at random here, where every vertex in V chooses D random neighbors from the vertices in U. Yeah. So in this case, if we have a subset of U of size epsilon, of fractional size epsilon, and we denote the neighborhood of the set as N of S, we'll be interested in sort of understanding the complement of this neighborhood, right? So which is sort of corresponds to gates. So S kind of corresponds to the gates that are set to 0 in U. And so the complement of the neighborhood kind of corresponds to the gates that are set to 1 in V. Yeah. So what do we expect about the size of the complement of this neighborhood? Well, we expect that its size is roughly the size of V times 1 minus epsilon to the D, right? So what's the chance that none of the D neighbors of V lie in this set S? That's going to be roughly 1 minus epsilon to the D. Okay, and the interesting setting of parameters for us for most of our constructions is the setting where D is roughly like 1 over epsilon times log 1 over epsilon, in which case the size of the complement of the neighborhoods are again an epsilon fraction of V. Okay, so this is sort of the most interesting setting for us, but indeed one can do this for any setting of P. Okay. And this is essentially the property of a random graph that we are trying to emulate in our deterministic construction. So we define this notion of an epsilon d eta neighborhood complement graph to be a graph where for every subset S, the size of the complement of the neighborhood is essentially what is expected in a random graph up to a small multiplicative factor, right? Up to a 1 plus or minus eta factor, yeah, which is one of the parameters defining the graph. So neighborhood complement graph is sort of one where the size of the neighborhood, and more importantly, the size of the complement of the neighborhood accurately reflects the size of the set S on the left-hand side. Essentially, it kind of emulates what would happen in a random graph with this kind of right degree. So that's the definition of a neighborhood complement graph. And the main de-randomization we need to do is to kind of construct deterministically these neighborhood complement graphs in a kind of an optimal way. Yeah, and this optimal way has to do with the size of V with respect to U. Okay, so let's just look at a trivial construction to see why this kind of restriction is sort of interesting in order to make the problem not trivial. So what we could simply do is to take V to be all subsets of U of size D. Right? So we could have one vertex in V for every possible subset of U of size D. And in this case, you can easily see that you get a neighborhood complement graph, right? Simply because choosing a random vertex on the right-hand side is equivalent to choosing a subset of size D on the left-hand side, which is exactly what we want to do in our random graph construction. And so this is kind of easy. So on the other hand, a simple randomized argument tells us that there exist neighborhood complement graphs where the size of V is not much bigger than the size of U. So it's the size of U times some polynomial in 1 over eta times log 1 over epsilon. And what we do in this paper is to give an explicit family of graphs where the size of V is the size of U times a polynomial in 1 over eta times a polynomial in 1 over epsilon. Right? So this is not quite as good as the randomized construction because the dependence on epsilon is much worse, but it's nevertheless non-trivial and much better than the trivial construction. Okay, and improving this 1 over epsilon to kind of log 1 over epsilon would allow us to sort of get an optimal de-randomization of the circuit construction of RS. Okay, so I want to tell you at a very high level how this neighborhood complement graph idea, how we go about this construction. There are essentially 3 ideas that make it work. And the first idea is sort of very classical and very natural in this context. We're trying to construct graphs that are kind of look like random graphs in some way. And there are classically known graphs with this property called expander graphs. So it's known that if you start with an expander graph and you look at walks in this expander graph, right, and use this to define a bipartite graph. So here, the vertices on the left are the vertices of the expander graph, and the vertices on the right kind of correspond to walks in the expander graph of some length, where each vertex is kind of represents a walk in the expander graph, and each vertex, and this vertex is connected to the vertices that appear in the walk of the expander graph, right? So now this kind of bipartite graph has all sorts of nice pseudo-random properties. So in particular, we know that these graphs have these walks have nice probabilities of hitting or staying in a certain set. And using this, we can kind of come up with some sort of very weak de-randomization of this construction of neighborhood complement graphs. Unfortunately, these constructions are way too weak. In other words, the size of V is way too big to be useful in our construction. So we cannot use these directly, but they sort of the first component of what goes into our construction. The second component is a beautiful observation due to Viola, who noted that one could use these expander graphs to construct these kinds of graphs that we care about in some way. But he showed that we could do better by sort of composing these simple construction that come from expander graphs together in a nice way, right? And this is an extremely beautiful idea, and I don't have a very kind of intuitive picture of why it works, but it turns out that when you take 2 such neighborhood complement graphs that are constructed using expander walks, but you compose them together in a natural way, right? So we have a graph G0 between U0 and U1, and a graph G1 between U1 and U2, and you compose to get a graph between U0 and U2 in the natural way by looking at paths of length 2 in this kind of unified graph, then you actually get neighborhood complement graphs with better parameters. So Viola's result is not really concerned with constructing neighborhood complement graphs, but you can kind of read this into what he does in his work. Right? So the second idea of composition, again, this plays an important role in the construction that we do. And finally, our final construction is based on doing this viola style construction for a large number of times, but this doesn't seem to be enough. Right? So we do this for a large number of times, but unfortunately we get neighborhood complement graphs where the sets in U1 are not as small as we'd like them to be. Okay, they are somewhat small, but they're not very, very small, which is what we need in our final circuit construction. So in order to get this final step to work, to get sets of really small size, we need to kind of do a one-shot construction of neighborhood complement graphs with slightly different parameters. And this sort of an algebraic construction based on the use of small bias spaces. So small bias spaces are, again, classical pseudo-random objects that are, again, connected to expanded graphs in some special way. And they've been used to de-randomize things like pairwise independence and k-wise independence. And we use a certain way of using small bias space to simulate pairwise independence, sort of motivated by some work in the PCP literature from this work of Ben Sasson, Sudhan, Badan, and Victorson from Scientific Co. And we use this to kind of pair, and we use this and pair it together with this viola style construction to kind of get this construction of neighborhood complement graphs that is useful in our circuit construction. Okay, so that's sort of a very, very high level picture of what we do, and I kind of defer details, the technical details, to the paper. All right, so that sort of brings me to the end of my talk. So just kind of a summary, we construct these neighborhood complement graphs to obtain optimal explicit formulas for the coin problem. There are multiple natural open questions. So first is to optimally de-randomize the circuit construction, which seems to be related to optimally de-randomizing these constructions of neighborhood complement graphs. And I'm kind of optimistic about this because they seem to be quite closely related to dispersers. And they seem to be slightly stronger than these classical notions of dispersers. And I feel optimistic that knowing what we do about disperser constructions, we should be able to get simple and better constructions of neighborhood complement graphs. And the second very interesting question is to come up with depth-independent hierarchy theorems for EC0 mod 2. So all the results I've spoken about so far give us size hierarchy theorems if we fix the depths of the circuit beforehand. However, if we want to separate circuits of depth 3 from circuits of depth 100, we don't really have problems that can do this. So can we show size hierarchy theorems that separate circuits of depth 3 from circuits of depth 100? That is an extremely interesting question that I don't really know how to approach. And that's kind of the main open question that I want to leave open here. Okay, that's all I wanted to say. Thank you.